Okay, now it should be on. Yeah.
Hello,
hello.
Okay.
You hear?
Okay. Yeah. Là c'est bon. Okay. Ok, de rien. À plus.
Okay. It's great. It's working, but not here.
Ici, no, parce que you are connected Wi-Fi.
Yeah, the connection.
Sinon, il n'y a pas de problème.
Si, il est long. Bonjour.
Bonjour.
Okay, so as you may not experience technical problems. Sketches, some game. So you can say up for tonight dinner, it could be at 7, not at 7:30.
No confusion, it's fine.
7 o'clock. The address is the gramophone.
Orsay.
I have been honest with telling you. I've been leaving out of Brazil more than I have lived. Yeah, I lived just like 6.5 years in Germany. And back to this.
Oh, right. I think we are live.
Hallelujah. Okay.
Good.
Okay, so okay, so thank you for being here. We're going towards the end of Tropicana. So two last talks, yeah. Don't be too emotional about that. So it's a great pleasure to introduce Paolo Scussolini from VU Amsterdam and Delta Res, right? With Paolo and Henrique, who is also here visiting from the Netherlands, we are going to explore a little bit more on the impact of storms. And yes, Paolo, the floor is yours.
Maybe we're not. Yeah. Okay, so it works.
You can just click OK.
Okay, then it disappears.
Disappears. Pero.
But I don't see that here.
It's on the other screen.
So,
yeah.
Yes.
Okay.
Thanks for bearing, and thanks for being at the last set of talks as well. So finally making a bit more sense of what I do, what our group does, and what we mean by impacts. Yeah, so I'll share the time with my colleague Henrique, who just joined Tropicana today and will be also here tomorrow. And yeah, this is work at our institute, the FU in Amsterdam, Institute for Environmental Studies, and also with Goulart, which is a large research institute in the Netherlands. And this is.
I don't know, Paolo, for the microphone, if you should stay around your.
Stay around here. It's less fun.
Okay. Recording.
I see. Now I see. Yeah. So you will remember this was the proud fruit of our brainstorming the other day, and we're not gonna tackle all of that today, but yeah, we just have the ambition of telling you a few key things about what we think key hazard quantities, surge, and flood, and what we do with that, and maybe yeah, I will tell you about the models we use and some global applications that I think are relevant here. And Henrique will go deeper into 2 case studies of those models and tell something maybe about exposure and vulnerability as well. Yeah, so surge modeling, straight into the beef. What we do is global surge modeling with the GTSM, model global tide and surge model. And this is based on the Delft3D suite of hydrodynamic models.
Paolo, for the recording, you should stay close to the microphone, or you can bring it here.
Bring this. Yeah. Okay. So this is a suite. The Paris. Excuse me. Okay. Well, I didn't have time for jokes, but apparently.
So we do it teddy bear shape.
Right. Maybe a bit more professional. Will you pay attention? Yeah, so I was telling you, that's 3D suites, so many solutions to solve hydrodynamic equations on 1D, 2D, and 3D indeed. And what's appropriate for the storm sources is the 2D shallow water equation, and that's based on this work. Because indeed, what matters most is what happens in the continental shelf approaching the global coast. And the key merit of GTSM is that it applies a flexible mesh, the FM flexible mesh, meaning that it solves at the 25 kilometers offshore, and then scaling with bathymetry, it goes to 2.5 kilometers unstructured grid towards the coast, and even half of that around Europe because we have better bathymetry. And the solution is at every 10 minutes step. So it starts with the finite element solution of 2012 of Alviso. And a good thing you can separate the tidal to the storm component or run them together. So allows for interesting studies there. And its inputs from your meteorological field, sub-daily, meaning ideally 3 hourly at least, or 6 hourly is also reasonable. But for you, these speeds and sea level pressure. So with that, you can train it on many things. And I'm going to show you a selection of global results. So the first surge analysis global was done by a colleague, Sam and Mouse, based on the era entering in the day, so quite poor, so much better, much more meaningful for the exotropics. And then this was refined further with the as era 5 became available. And Job Goulart compares in this paper a few TCs, and here are Irma and Michael around Florida, showing you how the say the surge amplitude increases as the resolution becomes finer. And since for a few hurricanes, GTSM with IFS also overshoots the surge that was observed. As you can see, the same colors here, observations and results. And then the most recent global product now is post-RP, which runs on the ECU on ERA 5 forcing, but acknowledging that ERA 5 quarter of a degree is not the best thing for tropical cyclones. It's enriched with synthetic tracks from the work of Nadia Blumenthal in the storm statistical approach. And yeah, and these are return periods for 1,000 years, tropical and extratropical storms with this, let's say, combined approach. Yeah, and also other things you can do, you can peek into the future. And that's what Sana and others have done. And I think this work with Malcolm also collaborated, of course, with 5 Iris Smith models. The extreme emission scenario here, And these are the results for the mid-century, how the levels for a 10-year return period increase or decrease into the mid-century. Yeah, and this percentage change. So it looks very, very interesting here, quite a lot of red. But yeah, if you look at that in absolute terms, it's not that much. And fun fact, you can also train that on paleoclimates. And that's work we've done recently. And this is the last interglacial. It's the warmest instance of climate we had, closer to this one, at least in the northern hemisphere. And these are seasonal results, same thing. So difference in percentage water levels seasonally. Indeed, it was a warmer climate during the summer in the northern hemisphere. And something interesting here, but again, the absolute terms here are not very high. And especially remind you again, this was a period where the hypothesis still holds that those huge boulders in the Bahamas were maybe hoisted by superstorms. And so I think there's still scope to understand whether, yeah, superstorms were plausible in that period, and we want to work at higher resolution with that. And yeah, so the surge, we're not happy with the surge, and we don't stop there. We need to do the flood explicitly, right? So, and yeah, when you have a global surge data set, yeah, the only thing you can do these days is, yeah, it's a simplified elevation-based routine for the flooding, and let's say make it a bit more sophisticated with an attenuation coefficient as the water proceeds inland. And this study, for example, has been able to calculate in principle, the exposure of global population to the 1,000 years return period of storm surges. And other studies have looked at the damage to buildings, and based on that also they can do adaptation work globally. That's too much to show. And rather, yeah, so if you look at that global map, you cannot zoom in. Yeah, it's very hard to see the flood maps themselves. On the other hand, that's what we have done with the World Resources Institute in Washington, D.C., with many others, distilling the results of these global studies and the flood maps themselves. And this is a web-based platform, you can easily find it. So the user here can have a first impression of coastal flooding. So you can also choose whether you want to look at coastal or riverine flooding, choose a return period in here, choose a time period into the future, and an emission scenario and a level of luck with sea level rise, let's say. And then zoom in anywhere in the world. And indeed, it's good for first rate assessment of hotspots of risk. Then, of course, when you want to really do work that's useful to a specific community, then you have to do something a bit more fine scale. And indeed, presenting you the model swings that we use, also mainly developed with Deltares. And yeah, it takes a number of static data sets as inputs, and then takes a meteorological input that would be precipitation, can be high extreme water levels at the coast, can be waves as well, and can be river discharge. And it's very suited indeed to handle these things in combination for compound flooding. Main merit here is that it can it solves rather than the shallow water equations, say the local inertial approximation inspired by this plot, so that you can have a really high resolution and do many iterations. So it's suited for stochastic modeling of floods, for example. And then we can use that indeed, and we will show you. I'm going to just show you a couple of slides of work we have in progress at the moment with a colleague Joshua Kiesel. We're looking at this in the Mekong Delta. It's quite a large area, and here it's fine to work at some 50 meters resolution with the Sphinx, and it's a very vulnerable area. It's subsiding. It's got agriculture there. It's also prone every now and then to typhoon passing. So yeah, we're putting now, this is a validation case for a concrete event in October 2005, era 5 precipitation, and seawater levels at different stations from GTSM 4 through era 5, and discharge from several branches, Global 4 through era 5. So we're working on that, and we'll do also scenarios of the future. Interested in seeing what, if you want to say something about typhoons there from your results. Another thing we're doing is, this is Naples. The Gulf of Naples at a larger scale here, and zooming in here. So Joshua is applying a pretty vast domain, and forcing that also to understand the components of flooding, so precipitation, from year 5. Then for the future would be Abdem, then would be downscale with Worf for 15 kilometers, and maybe and also a subdomain of 5 kilometers. The shortest from Absirk, also coherently forced, and also waves from the Wavewatch string model, also with a coherent forcing. And for the future, we want to do the impacts for the future, and based on that, see the effects of adaptation measures that can be taken. And these are things that the city is interested in doing: install breakwaters, Posidonia plantations. This is my only eye candy picture for you today. Very pretty, but likely, this thing is not going to do much to mitigate the wave effect. So we're going to suggest that submerged rigs and other things should also be implemented to a more meaningful mitigating, adapting effect. Now, Henrique, please.
Hello everyone. I'm a bit late to the party, just arrived. Nevertheless, I'm quite happy to be here. And when Paolo invited me to come, I thought of showing 2 case studies that we have developed. So technically, I think I see a nice intersection, because we are basically taking the atmospheric component of tropical cyclones and then modeling down to impacts. And from what I understand, there's a lot of people working exactly on the atmospheric side, so I see a lot of possible collaborations here. And scientifically, on the other hand, I'd like to also talk about storylines, which are the focus of my...
Can we point to the computer?
To the computer? No, I'm not trying to switch, it's just a point.
Sure. Right.
And so scientifically, the idea is to show up as well about storylines and how they can be used either for attribution or for future risk estimation. And then, so basically, the rationale behind storylines, the way we use is, first we look at some sort of extreme event, something that has caused large impacts somewhere in the world, so a tropical cyclone. Then we come to the type of question that usually people and stakeholders have, that is, how much worse could this be in the future? Or if this would happen in the past, would it have been less problematic or less damaging? And with this type of framing, we can take storylines, create what-if scenarios, and attempt to answer this type of question. And then the way we've done what we do here in Goulart and IBM, we create storylines basically with 2 ingredients. So the first one are the scenarios. So we create alternative scenarios, and you can create scenarios in many ways. The way that we try or we advocate for is that they have to be societally relevant. So things that society would be interested in could be climate related, but could be also vulnerability related or exposure related. So are we talking about sea level rise, or are we talking about expansion of coastal settlements in, let's say, Northeast US? Those things are equally important. And the second ingredient to build the storylines is a modeling framework. And that's the technical part that I talked before that I want to show. And Paolo has already shown some of the models. But basically, those 2 together, they make up the storylines, how we design them at least. And so the first case study, that's a study that we published earlier this year. It's on Hurricane Sandy in New York. So we basically created different scenarios of Hurricane Sandy and assess how they would impact New York under those different scenarios. So first, we have some 3 sets of scenarios. The first ones are climate scenarios. They're basically the NSAP global model that is spectrally nudged. So we basically change the upper layers of the atmosphere based on different global warming levels. And with this, we can recreate the event, but with different properties, but still the same event. We still see Sandy there. Then in parallel to this, we create different sea level rise scenarios. So they're independent from the climate scenarios simply because the timing of sea level rise is quite uncertain. So you might as well attribute them separately. And the last one that is quite funky is we to explore the effects of internal climate variability. We started playing around the track of the storms in order to explore how much worse they could be, not because of climate change, but rather because the track went like half a degree to the south or north, and how much worse it could be for the city we're looking at. So yeah. And then when we look at the modeling framework, how does it look when we think of the meteorological part that is here? So like the actual sending up down to the impact that we're looking at. And again, following the models that Paolo already discussed, we first take like mean sea level pressure and wind speed, we fit into this model that is GTSM. So basically we have the coastal boundary along the New York coast. Then we combine precipitation data with the water levels on the coast, and then we have a compound flood modeling. So water levels, they are produced both by precipitation and by coast surge. And finally, we click it on another impact model. This one is basically using OpenStreetMap to pick, to detect where like schools, hospitals, everything that's critical infrastructure, and how much water those assets would be exposed to. So that's pretty much the rationale behind the work. And then once you start adding the climate scenario or the different scenarios, then you have pretty much all the surrounds. So quickly on the results. So the atmospheric part of the results, the climate part, as I said before, with this technique of spectrally nudging the events, we can detect the same storm in every single scenario. And you do see some differences on the track, like at a local scale, it can lead to different impacts, but generally they behave quite similarly. And the main difference in the climate change perspective is that in the peak of the storm, peak of Sandy that was over the Caribbean, the warmer scenarios led to more precipitation, right, which is expected. However, when we looked at New York, since it was already in this extratropical cyclone stage, essentially we found no signal. So a higher, warmer temperature didn't lead to more precipitation over New York. And there's some reason for that. I discussed a bit on the paper, but pretty much from a practical effect, we decided to simply ignore the climate change aspect on New York because we couldn't pick a signal there. And we just dealt with them as alternative realizations, things that could have happened in both in the future climate, but also in the present climate. And then when we translate this type of atmospheric analysis to an actual hazard analysis, we start looking at all those scenarios together. And just to be very quick here, the idea, what is interesting is that we found out that the results can change a lot in magnitude. So we can have alternative scenarios that have very little flooding to scenarios that can lead to a lot of flooding. But more interestingly is that if we look at two scenarios that have quite similar magnitudes, because we're looking at a compound flood type of modeling, despite them being very similar magnitude, they were driven by different hazards. And the type of results is quite different. So here you can see the two graphs. The first one is a surge illuminated. So we see a lot of flood on the coast, and usually they come with high water levels. Whereas on the bottom, you see more widespread flooding due to high levels of precipitation. And then when we look at different climate scenarios, so we're going to start looking at, for instance, sea level rise. It's quite straightforward. The higher the sea level rise scenario, more coastal inundation we're going to have. And likewise, when we started shifting the tracks to maximize the type of flooding we could have due to precipitation, we'd see something similar for precipitation, quite meaningful values, but in the paper it's better explained. And finally, for the last part of the modeling chain that we have, when we look at the impacts, so we start looking at each type of critical infrastructure system. So if we're looking at, for instance, here on the left, at the power systems, if we look at a sea level rise scenario, so we have a lot of coastal inundation, then all the coastal power systems would be affected, and the implications for this could be quite widespread because those systems are highly interconnected. On the other hand, if we look at a different type of system like the road system, it would be more problematic or more impactful if we start looking at scenarios that have a lot of rain, because they don't need to have a lot of very high water levels to cause damage, but it's more important that they are widespread. So basically, the thinking here is that when we start thinking of how to adapt to different scenarios, besides considering like what type of climate or the future we're looking at, we also have to think of what the stakeholder is, especially if we're dealing with limited budget, which is virtually everywhere. So just to summarize, if we're thinking of seawalls to protect against the coastal damage of a tropical cyclone, for sure, power system stakeholders would be interested because most of the power supplies are on the coast. However, for the seawalls would do very little protection to the road infrastructure because it would still be like powering heavily due to the storm. And in that case, maybe the stakeholders would be more focused on like the drainage. Okay, so that's pretty much the results. I'm rushing a bit here because I don't have a lot of time. And then the second case study, that's a bit different. It's under review. This paper is not published yet. We're looking at storylines from the cyclone Idai in Africa. And the difference here is that we added some climate adaptation. So it's a continuation of the former case study. And now we add like climate adaptation to this framework. So again, different climate scenarios following that same recipe that I mentioned before, first scenarios and then a modeling framework. And we did a different approach here, but again, I don't have enough time, so we can always talk later about how we created each of them, but it's the same logic. So we nudge things, change things to have different scenarios that are plausible. And then we add this to a modeling framework with the addition of an adaptation component that is not linear, so it has some feedback. And this adaptation is basically motivated by local information. So we have the baseline type of adaptation, there's no adaptation. Then we have for in the coastal community what's called the hold the line. So let's know the kind of the Dutch approach. So let's build dikes around, let's try to protect everything we have. And finally, a more modern type of approach that is protect what you can and try to retrace or accommodate where it's possible to or harder to protect. And basically the idea is that we test everything as in the previous case study, but now we also test directly how climate adaptation can work. And again, just I think very straightforward results. The worst climate change scenarios lead to the largest impacts. Nobody's surprised here. And then, but what's interesting about this framework that we developed is that then we can start really looking even to like what impact the climate adaptation measures can promote. So for instance, here on the left, we see that in the scenario where we build dikes around, actually most of the cities is still exposed or still impacted. Whereas when we look at the other type of the more modern type of adaptation scenario, actually we see a lot of reduction. So this becomes very applied. So for stakeholders, for policymakers, this you're getting closer and closer to where like we can really relate and start getting closer to how they think and work. And that was intentional. And yeah, so that's it. I had to rush a lot. I hope it was possible to understand some parts of it. And if you want to look at the papers, there are some QR codes there. Thank you so much.
Yeah, let's take the word for one more minute, because I think we're doing great with time. We started very late. Do we? Just pick one of the things we want to work towards now is attribution, especially because if you review the literature, and I think I reviewed it well, I think there are just two studies that attribute tropical cyclone associated flood, not features of the tropical cyclone, but the flood itself. And this one is not much mentioned. So it's Zhang et al. 2018. They looked at Harvey, and they also looked at they used WRF and the land part of WRF. So to look at the local feedback of the urbanization to not just the runoff, but the rainfall, because urbanization has a drag to the whole TC system, so that probably played a role in solving that. So these are results with the urban and with the not urban precipitation, right? So it's much more. Yeah, so very interesting. Meister et al. Also looked at Idai, and they focus on displacement, so people migrating due to climate change. What would have happened? So This is the actual situation, just the counterfactual about climate change, I think just that. But yeah, both they use quite simplified spot solutions, so there is much room to improve that. And I think what Henrique does is already applying more advanced method. And indeed, so if you do flood attribution, so I said, showing you a visual that I made for real flood attribution, but I think it's quite the same, very similar for coastal flood attribution. During the time of global warming, other things have changed due to humans, especially. So things have changed on the land, land cover, upstream or downstream, the river basin. So closer or farther to the shore as well has changed. Yeah, levee constructions has altered the hydrodynamics locally. And yeah, this is less relevant for coastal, but yeah, irrigation and other things have changed, such that, especially if you are interested in working together with adaptation, you need a framework to look at each of them separately and in combination. So call them a framework for multi-driver attribution of floods. So that where you can tackle these conditional statements. What had happened if either of these was different, and what if everything in combination, and same thing you can do for the future. What if we do this? What if we do that? And how it will look like with future planning. And yes, finally, I think we're finished.
Thank you very much, Paolo and Henrique, for questions.
I have a question for you. I did not understand well why the borderline scenario fails at predicting city transforms.
Thank you for the question. That's a nice question. So here, right? So basically what happens is the storm surge is so strong that even if you try to build like a dike of 2 meters high that was equivalent to a return period of 150 years, something that is already quite unthinkable given the circumstances of the country, you would still overtop everything. And the reason why this other one on the right works is that because if you look here, once you start designing your walls like this, you leave a lot of space here and here for the water to to stay.
The dike is the same height in both.
Yeah,
sides.
yeah.
Thank
Yeah, so that great talks. Actually, a little bit about this for like the last day, or the last couple of talks. So I also had a question for Henrique about the Sandy simulation.
Yes.
Could you provide a little more detail on the model that is used? So you're saying you're using the NOAA model. So the reason I'm curious is because you don't get that period that Sandy intensified as it was kind of moving up the coast. It seems like if you look at that top panel on the right, you're well matched at the point where Sandy is making landfall. But I was curious, like, if you had any thoughts about the ideas of like whether the model was fit for purpose or whether it was capturing the dynamics well based off of that air kind of early forecast.
Yeah. So we use it's not NOAA the model. We use the NSAP from Max Planck Institute.
Okay, sorry.
It's a very good question if it's fit for purpose. In some ways, we can see here like it missed actually a lot of what was going on over the Caribbean. So in this sense, we decided to work on New York City before finding those things. So it was kind of lucky. Also because that's where most of the information for impact was available. So they didn't have anything in the Caribbean. And then once it comes over New York, then everything gets a bit closer. And actually one of the reviewers asked the same thing, like, okay, but if in one part of the, if part of the tropical cyclone is not behaving so well, should you still analyze it on a different part that it's allegedly working better? And well, there's a lot of
wasn't the review. So.
Well, there's a lot of experts here about this, but as far as I understand, the peaks are usually underrepresented by most models, especially the NSAP model had a 0.5 degree resolution. So it's not really like very high resolution. So it is a bit expected. And then once it translates into an extratropical state, then it's larger and then less. So it's a bit of a stretch depending on how you see it. because it's a storyline study, so we're comparing anyway internal simulations. Yeah,
Yeah, I mean, it's like I said, really interesting. We had a lot of talks last week about resolution and credibility and like how important it is for which aspects. And yeah, I don't know if there's a right answer. I just was curious when I saw the lack of the spike, but then it gets there. But that makes sense with it.
And
Grid spacing.
I test like, so yeah, as I said, this is from the MPI, this model, and I tested with different tropical cyclones, and honestly, most of them have the same thing. So again, Sandy, because it became a very large storm, I think that's where things start getting a bit better. But like, which tested like 20 or 25 different tropical cyclones, and most of them were not great.
Thanks.
No.
I have a question myself. So there was a talk well, also some papers by Eric Fisher in ETH that shows basically that precipitation doesn't really behave like other variables in the climate system. So if we look at millennial simulations, even in climate models, we see that, for example, we can have precipitation events that exceed, even without climate change, 4 times the maximum that we have already observed.
Yeah.
So how we can design things that last if already, then I mean, of course, this storyline approach we'll see doesn't change the fact that there is an increase of precipitation, Clausus Clapeyron or super Clausus Clapeyron, but still we can get because of the properties of the precipitation in the climate system events that are just a freak. And the Westphalia floods were probably one of these. So what's your thought about this kind of events?
Yeah, one thing they do is maybe the most suited way to look at that is this unseen approach, or is ours is the subselection of the iteration of the model results, and you keep picking where the circulation is going towards promising more rainfall and spawning more simulations from there. Yeah, that's the same thing with the northwest heat wave, complete freak, crazy return period event. Yeah, and it could be added in your scenario, in your storyline approaches in a productive way, I think. Otherwise, yeah, with precipitation, you've done the lateral movement, right?
Yeah, like the method is very flexible, but I think what is interesting about your question, and I think Eric I had a couple of talks with him about this, is also a bit of different perspectives that the different communities have. So I think from the atmospheric science, it's more straightforward to push more and more for the extreme, because you can do like stress testing or understanding the system. And then when we look at the coastal community, if you come with the craziest scenario possible, they look at it and say like, okay, fair enough, we cannot adapt to this. We cannot build a 15-meter high or tall dike. And that's where they say like, this, stress testing is interesting, but we cannot get out of this cost benefit framework. So actually I've been in some ways struggling, but in some ways enjoying this type of like this clash of perspectives, because I think storylines are much more accepted on the atmospheric community, but when I try to bring them to the coastal, or not necessarily coastal, but like flood modeling, they really have this typical reaction of saying, okay, but we need to do something that is going to be based on probability, because that's how you invest money. And I'm still trying. I hope one day I'll get to a point where we can conciliate everything.
Yeah, especially as coastal engineers that do the work itself, and its return period.
Just to add on this, in France there were floods like 2 days ago in Saint-Martin-Vésubie, the same the same place that was flooded by Alex Storm that Mireia studied, and all the things that were reconstructed from 2020, they collapsed again, and so they say like, that's what I mean. Then, yeah. So the very last questions, and then we can discuss the atmospheric river. So when you have source of moisture that comes from very far away, and your storylines don't take this into account, what do you do?
I follow that.
Like for example, the Bavaria floods.
Yeah,
which
so,
there are many.
Attribution has always been agnostic as to the object that creates the flooding in this context here. And we're just starting to think now in ways that, conditioning it to circulation condition to the storm object. Atmospheric reverb can be taken in that frame. Yeah, so there's detection that's possible. So some of the tools we look at that these days. But I don't know, it's not clear to me how, yeah, it was talked about how TCs can relate to atmospheric rivers and how that changes with climate change. Yeah, I don't know. And I don't know how we would make the storyline scenarios for that.
I would say, given the focus of storylines on being flexible, you can easily design storylines that have this. It's really about the scope. And actually, my supervisor Bart van den Henrique recently published a paper on exactly this event on the Dutch side, and actually transferring, because there was no like large scale typology that would prevent it from being translated to somewhere else. So there were no mountains in the Netherlands. They started playing around with this event, what they call like a water bond, and saying like, what if this event would happen on top of like Amsterdam, or what if it would happen? So you can account for those things. It's just it's gonna, at the end of the day, it's gonna be relative to the scope of this study.
Thanks. So let's thank the speakers again. So, why don't we reach, because we can take a few minutes for that. If there are more questions, we can take one more question. Yes.
So I don't know. You think you're interconnected to screen?
No, for yes.
You had mentioned one of your earlier slides that there's some storms that when you were forcing a surge model with, I think, IFS, that sometimes the surge was over predicted relative to.
Yeah.
So I'm curious
Can I share from my
why.
No, I think you have
get
to
that and when you get that, because I
connect
think
physically to this anyway. Because it's not using projector, it doesn't go for Zoom anymore for the projector.
My slides.
So.
Yeah, but you can share with your laptop, but you have to connect with this.
Something like that.
Yeah, I can. Oh, but I have an HDMI cable. We can.
This you need.
Yes, which I can connect directly to the HDMI, right?
Okay, yeah.
Using this.
Yeah, with the forcing rather than with the source modeling. Although there are.
So then I need to dial into Zoom.
And then you have to sit beyond it.
I have to zoom.
Yeah, the Zoom is for the recording now.
Ah, it picks up the voice from the laptop.
Yeah,
Yeah.
I think so. That's what I understood. Every day is different.
Oh, I'll just unplug for a sec while I start.
So I think that paper looked at 8 PCs, and that was everything for 4 feet.
Okay, so that's.
The overshoot. It's in the paper, yeah. And it's also there's some aggregated statistics of how much, how close it comes to the observed metrics.
Okay.
So go into Zoom. Log into Zoom. Okay.
Everyone got a chance to register for the online? So where is
With
the?
3 and 4.
That's to click the PowerPoint. Okay. Launch. Here it comes.
So
what is this, David?
Join with computer audio.
It's not yours. Okay.
Got it?
Yeah.
No? I think we're good. So the next speaker is Hamish Ramsay from Australia. And it's the last talk, right?
Yeah.
Yeah, so last but not least, so tropical cyclone risk, and we move to the Australian region, indeed. So this, I think you have to connect somewhere. This exactly.
There?
Yeah.
Nope.
Give it just 1 second. Let's click.
Oh. Yeah.
Yeah. Okay.
Doesn't matter.
Skip then. Yeah, I think you have to.
It doesn't matter because it's a Mac, maybe.
Yeah, perhaps let's try. No.
Oh, yeah. Now it's starting.
Okay, okay.
Good.
Okay.
Yeah. Floor is yours.
Do I need to hold this as well?
No, I think you can just, if you stay there, you can leave it here.
Okay. All right. Thank you. Thanks very much, everyone. Yeah, feel the pressure of being the last talk for the whole of Tropicana, but thank you, Susanna, in particular, for inviting me to come along. It's been really great getting to know everybody and discussing during the weeks and things like that. So anyway, I'm going to be talking about some work that we're doing in Australia to try to get a better handle on tropical cyclone risk. But when I say risk, I'm really talking about the hazard in this case. And so, yeah, just thank you to my colleagues at CSIRO below, as well as Chunsu Siu at the Bureau of Meteorology, who's been doing a lot of work on the regional model in the Bureau, which I'll describe in a second. So our approach is, so I stole this basically from Cha-Ying's presentation, similar kind of flowchart, but instead of hierarchical approach, I'm calling it multiple lines of evidence. So essentially what we're doing is using both synthetic TC models and regional climate models to try to understand the future behavior of, well, both current and future behavior of tropical cyclones in the Australian region. And these are forced by ERA 5 as well as a collection of CMIP 6 GCMs. So the two regional climate models that we're using for the project are the BARPA-R model. So this is uncoupled at 17 kilometers. There's a slide describing this in a second, as well as a model developed at the CSIRO called CCAM, which is a stretched grid model similar to MPAS. And it's at the moment configured to be 12 kilometers in the fine mesh, and then it expands outwards globally. And this is coupled. So we have one uncoupled RCM and one coupled RCM. The current focus is on SSP 370, and we're trying to understand global warming levels. So we're looking at 1.2, 1.52, and 3 degrees. We're using multiple trackers. So the focus mostly currently is on tempest extremes, but we also have one called the Surrey Direct Detection, which is one that Kevin Walsh developed back in the mid-2000s, I think, or maybe early 2000s, as well as the OWZ tracker that Kevin Torrey developed. And then the two synthetic models that we're playing around with at the moment is Jonathan Lynn's version of the MIT model, as well as a statistical model developed at Geoscience Australia. Okay, so firstly, just a very brief description of the Bureau's regional model. I'm not going to show any results from this model today, but I just wanted to introduce you. So it's run at 17 kilometers. It's over a fixed domain. So this is the top right, basically shows you the Cordex Australasian domain in red, and the BARPA-R domain, the regional domain, is in black. So it's basically very similar to the Cordex domain. Again, run at 17 kilometers, and I'm not going to go into all the details, but details are on the left. We're also doing some test runs, or I should say the Bureau of Meteorology are also doing some test runs at the moment at roughly 4 kilometers, so 4.4 kilometers. And those are nested within the BARPA-R domain. So it's called BARPA-C, so it's the convection permitting. And so far, they've only run a few of these simulations, but the production is set to complete in 2025. So the figure, the animation on the right is basically showing the difference between the Access model CM2 and the BARPA-R regional model. You can see that there's, well, here comes a tropical cyclone actually up in the top right that isn't in Access CM2. But the main weather feature is a quite an intense east coast low that developed as part of this trough, which I think we've probably already passed. But anyway, it spins up on the east coast of New South Wales, I think, soon. You can see it's, yeah, quite an intense east coast low that isn't really captured much by the GCM, as you might expect. Emma's done some preliminary analysis looking at the wind pressure relationship in the IB tracks, the convection committee model in blue, and the regional model at 17 kilometers in red. And you can see that the regional model has a wind pressure relationship that's to the left of IB tracks, and the convection permitting model is too aggressive at the moment. Like all the blue dots are to the right. So I was chatting to Malcolm about this, and he said, given that it's an uncoupled model, that's probably to be expected at this point. So it will be interesting to see what happens when they couple the model if the lows aren't overly deep at that point. So that's the regional model that the Bureau have developed. The other model that we're using more at CSIRO is called CCAM. It stands for Conformal Cubic Atmospheric Model, Semi-Implicit Semi-Lagrangian Atmospheric Model based on the cubic grid. It was originally developed by John McGregor in 2005, and I was impressed that Colin knew the reference straight away. As soon as I said CCAM, he said, "Oh, that's McGregor 2005," and hardly any, I'm sure he knows more than a lot of people in Australia about this model. Anyway, it is starting to be used more and more. It's primarily developed for regional climate research, but it's also started to be used for some weather forecasting and some process studies. It's open source, so if anyone wants to download it or play around with it, you can use that link, or you could email myself or Marcus Thatcher. We can tell you more about it. I'm not going to go too much into the stretched grid, but basically it uses something called a Schmidt transform to transform the grid from a kind of quasi-uniform grid on the top right to a stretched grid on the bottom right. There is still some issues with the bunching of the grid around corners, but Marcus is working on that at the moment to try to alleviate some of this bunching up that you see in the corners of the domain. Yeah, so as I said, this is coupled. It has scale-aware parameterizations for turbulent mixing, convection, and cloud microphysics. There is an option to, so due to the lack of the lateral boundaries, there isn't an option to use spectral nudging from the host GCM to assimilate information from the host GCM, or you could use monthly bias corrected SSTs with CCAM configured as an AGCM as well. So there's a few different options for this model, and I'll show you some results in a second. So this is not from our group. This is a study that was recently done by colleagues in New Zealand. So Gibson et al., they used CCAM to try to understand extreme weather events in New Zealand. And as part of their study, they also looked at a subset of tropical cyclones that developed in the regional model. So these are some of their results. So the top panel, top left, is the CCAM, the tropical cyclones in CCAM. The middle is error 5, and the bottom left is the IB tracks. In this case, you can see that the maximum intensity in CCAM is pretty similar to what we get in error 5, but it does, I'll show you the stretch grid configuration in a second, but it does produce more category 2 plus TCs, but it underdoes the really intense TCs. So the category 3 plus, there's only 74 in CCAM compared to a much larger number in IB tracks of 138. So interestingly, the translation speed, there were differences between the IB tracks and CCAM. This is because most of the tracks in CCAM spend more time in the subtropics and further south. So they have a tendency to accelerate more than IB tracks. So I think that's what you're seeing here. And you can see that here in the medium track latitude. So there are these biases that influence the track speed. In terms of some of the under-resolved nature of the tropical cyclones in CCAM for the New Zealand study, part of this is that the way they've placed the grid is they were very interested in extreme weather events over New Zealand. And so the grid basically starts to stretch as you go north. So in this tropical cyclone zone, we're already at kind of 15 to 25 kilometers. So whereas the inner part of the grid's around 12. So I think depending on where you place the grid, you get very different results. Okay, so our work. So this is credit to Sunny Trong, who's in our team at CSIRO. We've done some initial sensitivity tests just looking at a particular storm. So he chose TC Hina in 1985. I'm not quite sure why 1985, but this was the one that he started playing around with. And so the first set of panels is just comparing the error 5 tracks TC versus IV tracks. You can see it's a very good agreement in the track, but not surprisingly, it under resolves the intensity in terms of both the wind speed and the central pressure. So we wanted to understand the impact of kind of a quasi-uniform grid at different resolutions, so different grid spacings. So we've got 50 kilometers, 25 and 12, versus going to a variable grid at the same grid spacings. And so on the top right is just an example of the different grids. So we've got uniform, variable, and the bottom right I won't talk about. This is one where we just shifted the domain slightly to better kind of zoom in on the region of interest. So in terms of the quasi-uniform runs, the top left panel shows the minimum pressure, and perhaps not surprisingly, as we go to higher and higher resolution, so IB tracks is in black. 50 kilometers is looks more or less like error 5, maybe slightly improved. 25 and 12.5 kilometers are much better. So with 12.5 kilometers doing the best job at picking up the minimum pressure. Same thing for the maximum wind speed, but these are quite expensive to run, and so we did the same. And yeah, you can see the wind pressure relationship is also improved as you go to higher resolution as well, from the error 5 as well as the 50 kilometer in the top right, that blue curve. So yeah, so it's relatively expensive to run. So we did the same simulation looking at a stretched grid, which is much cheaper, and we found basically that we got very comparable results for this particular storm. Again, it's one case study, so we need to look at more storms to be able to generalize, but the preliminary results are promising. So again, once we get to 12.5 kilometers, we're doing pretty well as far as the statistical intensity of the storm, and the tracks all look pretty good for the variable resolution runs. So we also, so that's just basically saying what I said. We also started to look at the structure of the storm. So this figure shows the azimuthally average wind field over 48 hours around the time of peak intensity. So I think it was take the peak intensity, minus 24 hours plus 24 hours, and average over that window. Perhaps not surprisingly as well, as we, so first of all, the 50 kilometer run in both the stretched grid and the quasi-uniform grid under resolves the structure of the storm. As we go to 25 and 12 kilometers, we get a contraction of the wind field, as you would hope, and the storm becomes much more intense, and the radial inflow and outflow also increases in the 12 kilometer run. Okay, so that's basically almost done with the first part of the talk, and then I'll move on to some of the synthetic track models that we've been looking at. So this is just another result from the stretched grid and uniform grid, uniform grid runs for the same storm. So on the left, we're looking at the total heat flux with the radius in degrees on the x-axis and the total flux on the y-axis. And again, as we go to higher resolution, the peak of the total heat flux contracts radially inward and also increases in magnitude, and we get the same sort of result for the precipitation rate. So as we go from even 25 to 12.5 kilometers, we're getting more and more precipitation. Okay, so that's the first part. Again, we need to look at more storms because it is just one storm, but some of these results are still promising to suggest that we could, ideally use, say, 12 kilometers for our regional run, similar to what Marie-Dominique showed the other day for her region. And hopefully we'll get some fairly good statistics on intense tropical cyclones, which I would say are severely lacking in Australia at the moment. It's one thing the stakeholders always ask us is, what is intensity going to do in the future? And based on our previous CMIP 5 analysis, we don't have a good answer. So we're hoping that some of these runs, as well as the synthetic track simulations, which I'll show in a second, will provide some answers to that. Okay, so I won't go through the summary, you can leave that there. So moving on, the next piece of work that I've been leading is trying to improve a synthetic track model that Jonathan Lin developed using Kerry Emanuel's fast model for the Australian region. So I think a lot of people here have been in discussion on synthetic tracks and the CHAS model. So hopefully these components are now pretty familiar, but the MIT Lin model uses Genesis component, which is random seeding in space and time, but there's a basin-dependent latitude weighting. So for each basin, you can weight the seeds basically by latitude. So you can essentially statistically, prevent storms from seeds from forming too far equatorward, for instance, in certain basins. The track component is the advection plus beta drift, which is also intensity dependent in Lin's model. And the intensity model is two coupled ODEs, which is a CHIPS emulator. So CHIPS is the intensity model that Kerry Emanuel uses in his downscaling model. But so this is there's two coupled ODEs which basically emulate the CHIPS model. So for those, and if you'd like more information, the fast model is described here in this 2017 paper, and then the Lin model, Lin version of the fast model is in this 2023 paper. So moving on to some results for the Southern Hemisphere. So what I should say is I'm first of all trying to get a good representation of the Southern Hemisphere, and then I'm going to kind of filter it to look at the Australian region. So I thought rather than just zoom in on the region and try to, tune it just to get the Australian region right, I would see if we can actually get a better handle on the entire Southern Hemisphere. So this is just an example of the IB tracks plots on the top versus a set of tracks from the MIT Lin model. I haven't actually run that many realizations yet. That's one thing I want to do, is just increase the number of tracks so I can start to subsample, look at error bars and things like that. But you can see it's not too bad. There is actually, which I'll show you on the next slide, there's a kind of a positive bias in Genesis in the Pacific, in the South Pacific, and a slight negative bias in Genesis and storm frequency in the Indian Ocean. So that's one thing that would be nice to try to correct. So this is showing the Genesis longitude going from west at 30 degrees, which is basically close to Africa, all the way out to the central South Pacific at about 230 degrees. The blue bars are the Lin model, the stars are the IB tracks. I do need, as I've said here, I need to increase the number of realizations and add error bars on the blue bars so that you'd see more overlap with the observations. But you can still see, even without that, there's a tendency for the Lin model to kind of underdo the number of cyclones in the Indian Ocean and and produce too many cyclones in the South Pacific. So that's one thing we're going to try to resolve. So the next few slides are just statistics of various quantities that we've been looking at. So this is the Genesis latitude in the Southern Hemisphere on the left. And you can see there's a slight equatorward bias in the Lin model compared to the observations. Interestingly, when I look at the latitude of lifetime maximum intensity, that bias is kind of corrected somewhat. We don't see the same, equatorward bias in the LMI latitude as we do in the Genesis latitude. And I'm not sure, that may just be that the tracks are moving slightly faster to get to their LMI. I need to look into that. But yeah, pretty good agreement between the IB tracks and the Lin model for the LMI latitude, which is nice because a lot of stakeholders are asking about poleward expansion and the talk that we heard yesterday, for instance, it's very relevant. So it's nice that it produces a good climatology. This is the intensification rate over 24 hours. Again, not perfect, but it's pretty good. There is a slight bias, but at least in terms of the the positive, the intensification rates on the right, you see a pretty good agreement between the Lin model and the observations, especially, looking at rapid intensification events. The lifetime maximum intensity itself, there's a tendency for the synthetic model to kind of overdo the weaker storms and slightly underdo the more intense storms. So it doesn't capture this secondary peak in the LMI that we see in the IB tracks. But I was chatting with Jonathan Lin about this a couple of weeks ago, and I need to talk to some people who work more in the North Atlantic, but he was saying that this isn't as obvious in the North Atlantic region, this secondary peak. It tends to be more in the other basins. And so we're also wondering whether this secondary peak in IB tracks is I don't know, like potentially, well, I'm not going to say an artifact, but we want to look into this more because, we know that the North Atlantic has the best observations as far as airflow. What's that?
The storms in the Atlantic is not as strong as the Western Pacific, so, and it's based on the rapid intensification there, so it's very biased towards the Western Pacific.
Okay, thanks. But this is just Southern Hemisphere though, so maybe this is also the
That's why the Atlantic doesn't have so many,
Right.
have so many rapid intensifications.
Okay, so this may be that there's a lot of rapid intensification in, say, the South Indian Ocean or something like that. Yeah, okay, cool. Something we'll look into. Thank you. Seasonality, it's not too bad. It's slightly, there's slightly too many storms in the peak season in the Southern Hemisphere in JFM and not quite enough in the shoulder season. So you see it sort of drops off more sharply than in IB tracks. The right-hand set of figures is just a snapshot of some of some of the genesis locations in December, February, and April. You can see in February, for instance, there are storms in the Lin model that reach 35 knots further equatorward compared to IB tracks. And again, I was chatting with Jonathan about this bias a couple of weeks ago, and we were talking about the fact that in IB tracks, as storms move equatorward, they tend not to intensify, whereas in the Lin model, they can intensify. And so that's one of the biases that would be good to sort out. Okay, so I think if what's it, 23 minutes? Okay, so I think if there's one thing I want to get people to think about, and something I've been thinking about as well from the synthetic track modeling is can we use this for understanding seasonal predictability as well as changes in multi-decadal predictability? And of course, it relies on the synthetic model being able to reproduce the interannual variability. But so this is just looking at the Australian region now. So I've got the number of tropical cyclones versus time. And I was actually surprised by this result. So I've looked at others, even Terry's original tracks that he sent me a couple of years ago. I wasn't able to get anything near this kind of correlation with the observed time series. And so, yeah, and I'll get into some of the other issues on the next slide, but yeah, it's pretty good. Like, not only does it capture some of the really big years, but if you could imagine applying a sort of a smoother through this, it also seems to get the lower frequency modulation of the variability, which is interesting. So, okay, so now moving on to how this might relate to seasonal predictions and ENSO. The first thing to say is that in the Australian region, ENSO in the last 20 or so years has not been a good predictor, generally speaking, for tropical cyclone numbers. But before that, before roughly 1998, it was a pretty good predictor. So whether this is like the interdecadal loss, some sort of low frequency mode of variability that's changing the seasonal predictions, who knows? It could be, but so this again may be just a coincidence, but if you just divide the time series into two between the Lin model and the IB tracks, the first half of the period has a higher correlation than the second half of the period. And so I was thinking that if, for instance, ENSO is, modulating tropical cyclone frequency by changes in the large-scale environment, and the large-scale environment is the thing that's feeding into the synthetic model, then years where you have stronger forcing will be better simulated by the synthetic model than years where you have weaker forcing. So yeah, and so it's just I guess the thought to think that, you know, maybe we could start to use synthetic modeling to try to understand some of these changes in seasonal predictions. Interestingly, so this very strong La Nina event in 2010, 2011 led to the Bureau of Meteorology forecasting 20 to 22 tropical cyclones. And that year we only had close to average. But interestingly, the LIM model doesn't, despite the fact that we had a very strong La Nina that year, the LIM model doesn't give us a very large number like you would expect with ENSO. So, you know, maybe the synthetic models are picking up other things that are not just related to ENSO variability. So that's the other thing we could think about. So the right figures are just to show a study by Andrew Dowdy that essentially shows what I was just talking about, that in the early part of the period, the relationship was much stronger between both mean urine 3.4 and SOI, and with tropical cyclone numbers compared to the second half of the period. So something to think about. Finally, with my colleague Kate Arthur at Geoscience Australia and I have been thinking about landfall. This is kind of tricky in Australia because you get a very high frequency of intense tropical cyclones making landfall in this region in the northwest part of Australia. So lots of Cat 4s and 5s and a high frequency of landfalls to begin with. So this plot shows the essentially the probability of landfall as a function of these coastal gates. So moving from southwestern Australia all the way around to Sydney. And so that's basically what we're seeing here. So you can imagine, so this is basically going from left to right across the continent. And you can see that in the region around sort of Broome and Port Hedland, so this region in the northwest, where we have very high frequency of intense landfalls, the synthetic model is has a low bias, I should say, and it has a slight high bias for Queensland. So it's overdoing the number of landfalls on the east coast and underdoing the landfalls on the west coast. So that's one thing that we need to, I don't know, if we can try to kind of improve, especially once we start using it for impact and, you know, giving the information to stakeholders, we want to make sure that that we understand some of these biases a bit better. So that's it. So I'll leave the summary, but as I said before, I do want to know, I do want to get us thinking about the possibility of using the synthetic models as a tool to better understand the seasonal multi-decadal predictability of tropical cyclones, and also, you know, the potential influence of ENSO. So that's all. Thank you. I'll take questions.
Wait.
Hold on,
No.
Very thank you. My understanding is that the ENSO influence of Australia is stronger in the eastern part of the basin than the western part of the basin. And because the Pacific part is stronger related to ENSO than the South Indian basin part. When you did the change in the relationship of the ENSO with the Australian, would you separate also in different parts of Australia?
Not yet, but that's a good idea. But actually, the western part is the tracks off the northwest coast has a these tracks up here tend to have this region up here tends to have a stronger relationship with ENSO compared to the Coral Sea. I think it's the other way around, but yeah, it's.
The original papers from Nicholas Neville was the South Pacific Australia, the Northeast Australian dipole.
Yeah, so the original papers would focus more on the Coral Sea and the South Pacific region. But I think, you know, when you extend the data sets and you look at the more recent decades, the signal becomes stronger in the northwest.
So that
region.
changed too. So that's not my.
Yes.
You're saying that where the ENSO influence is changing too, so that would actually be interesting to look at, you know, if it's changing different parts Australia, because I'm assuming that environmental conditions would be very, patterns are very different regionally in the South in the Pacific Ocean.
Yeah, exactly. That's a really good point. So I think that's another thing we should look at is regional variability, sub-regional.
Well, so it is more a comment. I think two things. One is in the LMI distribution where you show there's a second, there's like you are questioning about second, which is fair because the way how the intensity, like how we define intensity in observations rely lots of things on how the process is doing. And maybe they do tend to increase a little bit, tend to go with higher numbers when the reality is not. However, I think if I remember correctly and correctly, so I saw in Kevin Reed's presentation a while ago, he showed an LMI from alpha plant simulation and also showed a second globally,
Okay. Yep.
not in specific region. And there's no forecasters influence in the alpha plant simulation.
Okay.
So yeah. I just found funny. Oh,
Yeah.
Let's know. Visual has to, yeah.
So it's probably, you think it's probably real, like,
Well, I mean, real or not is, we can continue debate, but the thing is this feature show up in alpha plan or not. So if you argue that it is about forecasters bias, then why is it show up in the model simulated lifetime?
Yeah. It's a good point, but does it show? So, I mean, I'm just going from what Jonathan said 2 weeks ago was that he thinks in the North Atlantic, it doesn't show that secondary peak isn't as strong. Is that true?
So is it because of recognition cases?
And the Western Pacific has more RR cases. Is that's your point before? Okay. I see. Yeah. Makes sense. That makes sense.
Yeah, so just one point. And the second one is the landfall statistic. I think that's something, how reliable downscale model can capture one real world realization. That's something we can discuss, but at the same time, how much do we trust the red point there? Does that represent the whole robust statistics?
Yeah, that's a good point. So there should be error bar. There should really be error bars on both, right? There should be error bars on the red points and error bars on the synthetic models. So that's a good point. Yeah.
I also had the same question. That it seems like your model is within the observations are within the possible reality of the model. So we have to close here because there is a discussion in 10 minutes. But you can keep discussing, and with this we close all the talks of Tropicana. So this is for all this. So I think it has been like 4 weeks of amazing presentations, discussions that you will find in the recordings of Tropicana. So that will be available for you to dig in and find answers of questions to your research, more questions perhaps than answers. So yeah, now we have a discussion on the pattern effects, if I'm not wrong, and projection uncertainties in the cathedral. And I remind you to sign up for the dinner tonight. That will be also the last dinner of Tropicana. And yeah, then for tomorrow we will prepare with the organizer some basic
people using like a aquaplanet,
Yeah.
there's no, so if you don't believe the energetic view and maybe you believe self-evidential view, maybe not,
no.
right? So
I do think the seeds are important. You know, like the number of seeds and the quality of the seeds are important. But
Quality of the seeds. Oh, now we went further. How you define the quality of the seeds?
so are you leading the definition of quality?
I don't know if someone else is going that direction, but one of the things I would like to do in like a medium-term future when I can get my hands on model would be to do some idealized simulations either in different climates or tweaking some variables, or I don't know, playing with the continents or that kind of things. And that's one of the questions I'm personally very interested in. I would like to explore using very idealized simulations too.
yeah, I like that. I think we can make progress by doing more idealized genesis simulations.
Yeah, you found the global PC frequency, it's very different from what you see in the real atmosphere.
Yeah. I think so getting back to the real atmosphere, I think to understand the frequency problem, we need to understand the mechanisms in each of the different basins. So, for instance, African easterly waves, ITCZ, you know, instabilities and vortex roll-ups and MJ, all the different, so maybe going back to the underlying large-scale circulation perturbations which lead to the seeds, which leads to genesis, and maybe understanding those features might help in the real world. But and that's basin dependent. So
do you think there's any promise that going to order kilometre scale will converge for a bunch of models, would converge the number of tropical cyclones the models produce, or is that just not going to happen? No.
I don't think so.
Do we know, like, the years that have more storms globally than like, if there's a year with 110 and there's a year with 70, do we understand why those years have more and why those years have less, or is that like unknown?
Good question.
What was the question?
Do we have an understanding at all of like why certain, like the years that have more than average globally, the years that have like 100, 110, do we understand why that occurs in that year versus the year that has like 70?
I think that the numbers are heavily influenced with the Western North Pacific because, you know, has so many. So when you took in the global, if 33% come from of the storms come from the Western Pacific. So that thing, so if you take out the Western Pacific, then, you know, you're starting having other issues.
So is the time series of global TT frequency highly correlated with the time series of Western North Pacific then?
It's only really good to answer.
Yeah.
Pensacola has a paper looking at global TC then.
Okay. And Bill Frank
has like all the basins and how they connect with itself, because you have one basin increasing, the other basin decreasing, so you have this.
But didn't Bill Frank argue that it wasn't compensation in the end? Because some people were saying there's compensation between the different basins, which gives you a relatively steady number. But I thought his paper was saying that he wasn't advocating compensation.
So I think the compensation is clear, like in some basins, like you have like the Atlantic and the Eastern Pacific, it's a very clear anti-correlation. But then when you go to other regions, it's not as clear because, for instance, the Western Pacific, the ENSO signal is basically not in the numbers. So
it's like the South Pacific, it's not in the numbers, it's just in the spatial, or where they form.
There is combination further to understand if there's a basin feedback, like you're studying. If the passing of one makes the ocean more or less propensity of having force, that would be critical then.
Now, I guess my question motivated by, can we use the kilometre scale models to tell us something that we can't do by running long simulations, but that would complement the things that we can learn running 10, 20?
The answer is until you run them, we probably don't know. Like my experience with running the WRF, which is obviously not at the global scale, is that I find it very hard to not spin up anything non-developing disturbances, I find very hard to not spin them up in the WRF model when I'm down at millimeter scale.
Right.
So, but going back to what I was saying about tuning models, even the kilometer scales models, you still have a lot of parameters. So I don't know, you know, how much you're going to learn because if the different models still are tuning different ways, even if you're not dealing with the convection, you're still tuning other things. So,
but I think we get better structures out of it for sure. And if we're down,
and
if we're down to resolve, you know, if we're down to resolving, we can couple to an ocean. Maybe that's part of the answer for the difficulties I've had in the past in Europe.
I think some of the studies have looked at ocean eddies, small-scale ocean eddies impacting these high-resolution couple models and how they affect tropical cyclones. That's how at least how I see the use of high-resolution models of understanding the process of the same.
Right. But yeah, I was coming back to we're not. Maybe we don't want to run kilometer scale models for climate, but yeah, are they a tool that we can use to understand?
Yeah, potentially.
But I've been thinking about ways to combine a large ensembles, machine learning, and high resolution models. I have this like very broad, very initial idea with just looking at maybe like, for example, CSM large ensemble, like Lens 2 or something, and then apply a statistical like Shaz model to the large ensemble, and then use causal discovery, Tom is an expert in, to try to understand, the controls of tropical cyclones in large ensembles and how climate variability affect these controls and things like that. I just feel like the large ensembles is of great values, but of course there's uncertainties of the downscaling large ensembles. Will it introduce a lot of uncertainty in these questions? Still exist, but I think it would be a great starting point.
But whatever, just keeping in mind all the time that whatever bias the CSM have is going to trickle down to everything.
Exactly. Yeah.
The value of the ensemble should be that hopefully, you have ones in which seeds aren't there or don't develop, and seeds are there and do develop, and then you can explore the environmental controls on that. That's the value. That's one of the values of the ensembles.
Yeah. For example, for the SSC warming pattern, they also have a different driver. One is like a uniform warming, another is a pattern warming, another huge impact in internal variability.
Yeah.
Then how there is already some like a hackathon thing to combine different groups to take part in this kind of project to use different kind of machine learning or some the traditional statistical model to try to disentangle like this different uncertainty to its contribution to the SSC warming pattern. So I'm not sure Tom has some idea on how to use machine learning to help us to understand different uncertainty in the TC projection.
I think there are projects trying to do this, but you always need a baseline, right? So what would be the baseline statistical technique to understand uncertainty in which variable?
Yeah. And also we assuming like a climate model can have already present something, and we like what I see people do is they use a large ensemble simulation to train the machine learning model and then change the input as observation and to do some like emergent constraint study. I'm not sure if we also can apply this kind of method to TC.
That's interesting actually to ask what people think about the emergent constraints framework in the context of TC projections, because I want to learn more about how people think about it in this community. In the people who do climate TC projections, what's your opinion on the emergent constraints as a framework? Are you worried about it? Do you think it's underused?
I'm under the impression that you need a large ensemble of projects of models to apply. but I'm not sure. I know that we don't have enough TC permitting simulations anyway to apply this kind of framework.
I guess it's a good question for the high-risk researchers. Are we getting to the point where we have enough, well, high-resolution simulation that marginally resolve TCs that we can start thinking about emerging constraints for certain characteristics of TC activity, TC tracks, etc.?
So how much data do you need? I don't know. They have never done.
Yeah.
It
really depends the kind of constraints you're trying to formulate. But I'm not exactly in that subfield, but my understanding of it is you derive a statistical relationship between two variables, typically it's between one you know about and ECS and TCR, and then you use observations to then constrain the uncertainty you have, assuming that relationship holds true. And then there's recently, people have adopted a more machine learning perspective where you use the fact that high resolution model output has higher frequency, so then if you frame it cleverly, you can have more samples to train with and then get better uncertainty rounds. But I think that's a good question for people doing high-risk MIP simulations as to whether we have enough models to.
Yeah, well, but I think the problem there, right, is that most, if not all of the high-risk MIP models, for the most part, projected a decrease in TC numbers, but we know that from other work, depending on how you do the humidity, you can make them go look down or up. And so we kind of have this fundamental of the models would suggest they're going to go down, apart from, maybe apart from one or two models. But depending on how you treat the humidity, other methods could say they go up or down. I don't really know how you get past that.
So could we constrain maybe on the representation of answer and what you've been showing the Columbia group to select models in emerging constraints framework?
I'm not an emergent constraint expert. I'm very intrigued by the idea because I think it's a way to use high resolution model output statistics and observations to constrain some of our projection uncertainty. But I personally have sort of read the papers, but I'm barely starting to use it in some very restricted cases with SST where, too much paper. So I don't know what you were saying. I mean, it sounds like it was not for TC frequency, it wasn't even relevant because like if the observations go one way and all the models go the other way, then what are you going to learn? You're not even within the range of what the models project, right? So it's then your conclusion is like we can't. Well, I think what you could do is you could look at what the models do well. I think that's what people do. You look at what the models do well and constrain on these variables to reduce the uncertainty range or make arguments as to why certain models are why certain models are potentially more trustworthy than others with respect to a specific process, but maybe it's,
Yeah, I think just jump in when you can.
I was just looking in the most basic sense, the way you describe it there is that you just sense, you're trying to find a linear correlation between something you know about the models and what projection they do, and you want to extrapolate up to the observations. So if you can find a relationship between why the models are predicting lower or higher, you just extrapolate up to observations. That's your measure straight, like in the most basic sense, right?
It's not linear, right?
Well, it might not
be linear. You could start with linear, but often cases it's not linear, right?
The question is there enough models? Must be enough different models to do that relationship, and needing more, I guess, if it's not linear.
All right, we're coming close to the end of our time. I wanted to see if there was anyone who hasn't felt like they could jump in and say something who wanted to give you the opportunity without putting you on the spot by picking on people.
I would like to talk about the uncertainty of the landforms. I know that there are many things around the climate environment and everything that are important in terms of quantifying the uncertainty, but I think we should also talk about the uncertainty on the landforms because in terms of risk is the most important part of the project. So I don't know at least how to quantify that or how to track this uncertainty.
In terms of observations or in terms of projections? Because there is uncertainty in terms of the landfall observations as well, right?
For projections, it would be great. But yes, I mean, because if we compare any synthetic tracks data set, the results are going to be different. So that can change everything in terms of impacts and risks. At least how to quantify that, how to correct.
Has anyone looked at that? Amy has been doing a lot.
I mean, so uncertainty quantification, what I'm doing is usually you have a sufficient number of data sets, synthetic events, or global stone tracks from global kind of models, and then you can separate them based on the different categories of the uncertainty you want to address. So if I want to address the uncertainty that is associated with the interannual variability, then I look at the ensemble spread caused by interannual variability. I want to address the uncertainty caused by the different model, different approach, that's called model uncertainty. Then I look at the spread caused by model uncertainty. And of course, there's also scenario uncertainty. So you kind of bring all the data together and then you look at the uncertainty due to scenario. So one of the slides Jing showed, showing those green, orange, and the blue plots, they actually have one equations help you to how to kind of linearize the contribution of different type of uncertainty. And that's one approach. Also, I think just maybe it's interesting for the group that.
So in terms of landfall, don't you what you're doing with Aeon and stuff like that? Because I think that's what she's getting at.
Yeah, but that's the same idea, right? So because you just focus on your landfall, you get the spread based on different data sets. I mean, if you are asking about the observed uncertainty, then one thing is you sample the data in your model data based on your observed frequency. Then you get a spread that's showing you what's the reasonable range of uncertainty from the sample error that you should see. You should see along with your observed value. So one thing I think is interesting to know is different synthetic model, they have just like a different global kind of model that have different kind of sensitivity. Different synthetic model, their sensitivity to different source of uncertainty is also different. Like a Keras model is very sensitive to the choice of global kind of model. And in this at the baseline white value. Well, I say that I should say is actually the value, so for stone track. And the chess model is like a most sensitive is actually SSP scenario. So is the stone. It's less sensitive to the GCN. So that's something kind of good information to very few try to talk about uncertainties. And so you know you are based on the data sets you are using them. They will be happy. I can put this. So
I know about this paper. Yeah,
in the last paper.
Yeah.
At least that's how I will do. I'm pretty sure there's people have maybe made an approach straight. To me, that's how I would.
I think the other thing we can do is, someone mentioned this the other day, is to compare different modeling approaches. So, for instance, synthetic projections versus explicit tracks projections. And then, so if we use multiple methods and multiple approaches, it hopefully will help convey the uncertainty. I don't know what the paper was, but I remember seeing a paper a couple of years ago where they looked at synthetic track projections versus explicit tracking, and they found that, for instance, in the synthetic model, there wasn't much change in the LMI, but in the explicit tracks, there was an increase in the LMI. So I think things like that would be useful as well.
Anything else?
We're going back to something we said at the beginning. Is this a venue where we can lobby for, in the new Iris MIP 2 iteration, that all these things that are data heavy, that the routines that can be run online, rather than downloading afterwards, or begging people to save at high resolution timestamp. Is there a way that can happen organically?
Could we start a list in Slack that we sort of dump on you, Malcolm?
Yeah.
Yeah.
I mean, we have
Way to do that?
for the high-res MIP2 paper. We've kicked the data kind of down the road because it was too complicated. So for example, we are the modeling groups run a given tracking algorithm, so that each modeling group at least produces the tracks consistently, because they have the data right there, rather than again trying to convert and upload the 6 hourly data, and then someone downloads the 6 hourly data and actually do it at the time. But yeah, I mean, obviously, as you know, for these models, the more variables you ask for, the more difficult it is to run the simulations and store the data. So if you can, we want this output, it might need really high frequency data, but the output is much lower density and easier to like I was saying, running the static modeling. Then we can certainly take that and try and look at the model.
Your own idea that we discussed at breakfast. Indeed, sounds phenomenal.
So we can certainly try that.
You can also talk about doing time slices that you have more process diagnostics.
Are you going to use global warming levels for your time slices?
Yes, yeah. So we're going to do the last 20 years of the AMIP simulation, and then on top of that we'll do the
2 degrees or something.
I think 2, 3, and 4 we plan with an El Nino like and a La Nina like pattern, if we can figure out how to do both of those. But that would be an idea.
But you also mentioned having like a couple of years or 1 year or whatever, to have a lot, list of high frequency data that you can do, like process diagnostics that we are talking about, like.
But then there's variability anyway, right?
We can certainly.
You can do every.
We can certainly ask for that, but I mean, it does get hard for the modeler groups to kind of switch on and off different diagnostics in different years. But we can have it as a kind of higher level on the data request and see. I mean, I know your experience that the groups can say yes, we'll do this, and then when it comes to actually running the simulations, they're hard enough as it is without adding lots of extra things. But we can have a list. Yeah, if we've got a list, then at least we have something.
What is the number of models you expect to participate in Iris MIP 2, and how does it compare to High-Res MIP 1?
Well, so I mean, High-Res MIP 2 is still only an idea. We haven't published the paper yet that will describe the simulations. High-Res MIP 1, we had about 7 couple models and 10 to 14 atmosphere only. So hopefully that kind of level at least.
All right, why don't we close it there and go to lunch? Thank you, everyone. I thought it was a
very much.
Just a reminder that we will have a TC/model evaluation discussion at 2 p.m. Same place.
There will be a lot of overlap with this discussion, so we can just continue some ideas.
And thank you to Henrique who put that together.
Good. Thank you both very much. That's fun. Yeah, great. Yeah.
Thank you for leading the.
Wow. Hooked in a couple of questions.